Hello and welcome back to my channel. Today we're going to be talking about implicit differentiation, but kind of like a day two, so just some more practice problems and different ways we may see problems. So something that's commonly shows up on the AP test as a free response question is consider the curve given by x times y squared minus x cubed times y equals 6, and show that dy over dx is equal to this specific derivative. So these types of questions show up quite often, and they are ways of giving an equation and being like, hey, here's the answer, show how you get there. So realistically speaking, we're going to do everything we would have done normally. We just now have an answer that we need to show that is the same as. So the first thing we're going to do is take the derivative of our equation with respect to x. So if I look at this first piece here, I have x times y squared, so I need to use product rule. So u is going to be x, v is going to be y squared. So u prime is going to equal 1, and v prime, the derivative of y squared, is 2y, and because it's a y instead of an x, dy over dx. So we have 1 times y squared, so y squared, plus 2y dy over dx times x, or 2xy dy over dx. I wanted to write it like this just because I feel like it's easier to kind of read instead of having the dy over dx in the middle. And then if I also look at what I have over here, 2xy, 2xy. Our next part here, we have the derivative of negative x cubed times y. So this is another product rule. So we're going to use u and v again. This time we have negative x cubed. Actually, for consistency, we are going to actually use f and g. So f is going to equal negative x cubed. G is going to equal y. So f prime, we have negative 3x squared. G prime, we have 1 times dy over dx. So just dy over dx. Okay, we're going to put that in now. So we have minus 3x squared y plus negative, so we can realistically get rid of that. We have an dy over dx times x cubed, so x cubed dy over dx equals the derivative of 6, which is 0. Okay, now all we're going to do is what we would normally do. We need to get dy over dx is on one side. We need to get everything else on the other. So the one thing that I want to kind of keep in mind is what's positive over here. So if we're looking at our piece here, our 3x squared y is going to be positive. It's negative right now, so we're probably moving that over to the other side. Our y squared is negative here, and it's positive here, so we're probably moving that to the other side. 2xy is positive, and it's positive. And then we have that minus x cubed. So I'm going to keep dy over dx on the side that it's already on, and I'm going to move everything else to the other side. So we're going to subtract y squared, and we are going to add 3x squared y to both sides. I'm changing that plus a negative into just subtraction to make it a little bit easier on us. And then we have 3x squared y minus y squared. Okay, we have dy over dx by itself in our two terms, and we have two of them, so now we want to make it into one. These two terms have a dy over dx in common. They also have an x, but we don't need to get x by itself, and it's not factored out here. So we're going to go ahead and factor out a dy over dx from both of our terms. So dy over dx times. When we do that, we're left with a 2xy and an x cubed, and this side stays exactly the same. We now have dy over dx times everything else, so we're going to go ahead and divide both sides by the stuff inside the parentheses. So we have 3x squared y minus y squared divided by 2xy minus y cubed. So now we just want to double check to make sure that all the signs are the same, everything that we got has the same. And when I look at these two, they are identical, so we know we are good to go. Find all the points on the curve whose x-coordinate is 1, and write the equation for the tangent line of each of these points. So we need to find a couple different things. So we need to find equations of tangent lines, which requires us to do a slope and an intercept. So I already know that I'm going to need slope, which is our derivative. But we need to figure out where these points are. So we have an x-coordinate that is equal to 1. So we're going to look back towards our first equation. So we're looking at the original equation, which I'm going to write right up here, x squared, x times y squared minus x cubed times y equals 6. So we want to figure out any time the x-coordinate is 1. So the first thing I'm going to do is I'm going to plug in 1 for all of my x values. So we have 1 times y squared, so y squared, minus 1 cubed is still 1, so minus y is equal to 6. We only have one variable now, so what we're going to do is we are going to move the 6 over. We have an y squared and a y to the first, so we know that we would have to factor in order to do something with this. So I'm going to subtract 6 from both sides to get this. So we have y squared minus y minus 6. We're going to factor this like we would normally factor anything else. I need to multiply to get to negative 6, and I need to add to get to negative 1, so negative 3 and positive 2 are my y values that we're looking at. Setting these both equal to 0, I get the fact that y is equal to 3 and y is equal to negative 2. So the two places this happens is at the points 1 for x and negative 2 for y, and 1 for x, 3 for y. So we have two equations that we need to write. So we have two things that we need to find the derivatives of. We already have the equation for our derivative, dy over dx equals 3x squared y minus y squared divided by 2xy minus x cubed. So we're going to take these 2 points and we are going to separate them. So we need two equations in the end. So the first equation that we're going to be dealing with is at the point 1, negative 2. So dy over dx evaluated for x comma y equaling 1, negative 2. So I'm going to go ahead and plug in my x values and my y values. So my x value is 1, so we have 3 times 1 squared. Y is negative 2 times negative 2 minus negative 2 squared divided by 2 times 1 times negative 2 minus 1 cubed. So we're now just simplifying. So we have 1 squared, which is 1. We have 3 times negative 2, which is negative 6. We have negative 2 squared, which is 4, so negative 6 minus 4. We have 2 times 1 times negative 2, which would be negative 4, and 1 cubed is 1. So we have negative 10 divided by negative 5. Thankfully, this is a really easy number, so this is going to give us 2. So we know the slope of our function at the point 1, negative 2 is 2. So I can go ahead and write my linear equation. So we have y minus our y value, which is negative 2, so plus 2, equals our slope, m, times x minus our x value. So I know that this is going to be one of our two tangent lines, and now I just need to find the other one at 1, 3. So we're going to do the same thing. dy over dx evaluated at x, y equals 1, 3. So we have 3 times 1 squared times 3 this time minus 3 squared divided by 2 times 1 times 3 minus 1 cubed. So thankfully all the stuff with ones are kind of a moot point a lot of the time. So 1 squared is 1, 3 times 3 is 9. 3 squared is also 9. Dividing it by 2 times 3, which is 6, minus 1 cubed, which is 1. So what we have here is 0 over 5, which is 0. So what this is telling us is that the slope at 1, 3 is 0. So if I wanted to write the equation of a tangent line, we would do y minus our y value 3 equals our slope 0 times x minus 1. This is a valid equation. There's just a lot of extra stuff. So we know if we were to move this over, all of this 0 times x minus 1 is going to go to 0. So if we add the 3 over, we have 0 minus 3, or 0 plus 3. So y equals 3 would be our other tangent line. So the big piece here is we had our derivative and then we just needed to do something else with it. Finding those tangent lines are really easy things that they would ask you because we just need a slope and a point, and knowing that derivatives is a slope is going to be the big key there.